All right. Okay, so good morning, everyone. I'm going to try to go a little bit further beyond what Gert was talking about and start introducing the concept of segmentation and regression. Okay, I'll try to get a little bit closer. Maybe that will help. Right, so talking about segmentation and regression as two of the most common tasks that people normally try to do, at least within the MICCAI community. This is something that is very common in our field. So before I go there, I need to start by talking about deep learning as a regression problem. So if you think about it, most of the times what you have, the problem that you're trying to solve is to map some input, which is in the space of Rn. So you have an image which has a certain cardinality. And the idea is to map that image from a space to another space. And if you think about it from a mathematical point of view, that's nothing more than taking a vector which has some intensity, some images. And that vector is going to be mapped to an output space, which is going to be of the same cardinality. That's what segmentation is. Or it could be of the or just a space of, for example, a categorical variable. So this is what classification would be. So for example, if you have a multi-class classification problem, I'm not talking about segmentation, I'm talking about classification. For example, detecting if a picture is of a dog or of a cat. What you want to do is take an image and map it to the space of a single categorical variable from 1 to k, when you have k classes. If you are, for example, trying to solve a regression problem, the problem is actually pretty much the same. The difference is that the output, rather than being categorical, is an output that is in R, right? It's just a continuous floating point variable that you want to predict. That could be predicting the age of a patient. That will be a type of regression problem that you could have. But the interesting thing from all of this is that pretty much all of these problems can be seen as regression problems. At least in the supervised setting, they can mostly be seen as regression problems. Denoising is nothing more than taking an input, perturbing it with some noise, and trying to recover the original input. Again, that's a regression problem. One-class classification is trying to regress some form of distance from a compact cluster. Again, you can see that as a form of regression problem. Pretty much all of these things can be seen as regressions. It's just transformed versions of the same thing. So what changed with deep learning when it started was that with classical ML, intensities themselves, the images themselves, were not very good features. So most of the work, as Gert was saying, was about extracting features to represent the data. So we were trying to have this form of representation learning by we, as humans, trying to give meaning to the images by extracting something that we felt was semantically meaningful. And then, after we had this representation, there was a mapping function from input to output, so from feature space to the classification or the segmentation. That was the last step. And this would normally resort to tools like support vector machines and random forests. And what happened with deep learning was threefold. Obviously, data became bigger. Medicine is now digitized, so we start having more data. The tools became better, and now we have GPUs available, so we can compute faster. We can have tools that auto-differentiate, which means we don't need to solve for very large problems. But more important than that, the idea of representation learning became extremely important. And really, the idea in representation learning is that these two tasks that used to be done separately, extracting features and learning the mapping to the output space, are now learned together. So the network not only represents the features, but it represents them in a way that is optimal in order to be able to map that input to the output space, be it a regression or a classification problem. So they are pretty much the same thing, just the deep learning approach does both jointly. And the way that it does it, in a really simplistic way, and I like to say this as a joke, is that what you basically have is you take an input X, and you just apply some function that transforms it, given some parameters, omega 1. And then you take the output of that and you transform it with another function, and you transform it with another function, and you transform it with another function. And each one of these functions are relatively simple, but when you compose many relatively simple functions, you can have extremely highly nonlinear functions that can map pretty much any input to any output space. So the problem of deep learning is nothing more, again, in a very simplistic, very generalized way. How do we put building blocks together so that when you concatenate them, when you compose them together, how do you map that input to the output space, right? So if you now think about what classes of functions should we be looking at? And that's a really interesting question when we start thinking about the kinds of things that we want to do. Right. But before we go there, so the three main building blocks when we try to design these systems, most people think about these three components. The representation part, the network, and that represents things like architecture. We need to have considerations about scale. You need to have considerations about the depth of the network, how complex the functions you can model are, how wide the network is in terms of the number of features that it has. Does he have enough capacity or not to solve your problem? The second part, obviously, is the loss function. The loss function is extremely important and is actually associated with the problem that you want to solve. And we're going to see that there's a couple of relatively simple ones that you can rely on. And the optimizer. And most people think about the optimizer as solely optimizing a loss function. But actually, the optimizer itself is part of a learning process. And you'll see later on that the choice of optimizer and exactly how you optimize your function can completely differ in terms of results and the generalizability of your networks and of your methods. Right, so as I was saying before, these two problems are pretty much the same. Multi-class classification and image regression is pretty much the same. You're mapping something from Rn to K or mapping something for Rn to a variable Y, which is nothing more than a variable in R. And they are the same thing because if you actually take the equation at the top, that mapping at the top, you can also see it as something like this. So you're mapping an input from Rn to Rd, where D is, or actually that should be Rk, where K is the number of classes. And then you're putting that through an argmax function, which is taking the value that is the higher, or a softmax function, which is going to give you a probabilistic output. And that then gives you a categorical variable, right? So the mapping is pretty much the same. It's just in the segmentation case, you have this extra step where you're basically squishing your predictive outputs, in that case the logits, and you're transforming them through a softmax function or an argmax function to give you the output that you want, which is either a probabilistic value or a categorical value. Yeah, I can skip that. Right, so when it comes to building blocks, as Gert was talking about, there's many things that you need to decide. And it is still a little bit of an art rather than science. There's many types of hyperparameter tuning that needs to happen, a lot of tweaking that needs to happen. But there are starting to now exist algorithms that can optimize some of these things for you. But you have massive choice of activation functions, all of them with different properties. Different activation functions provide different kinds of properties that you want. For example, if you have something as simple as a ReLU, as Gert was talking about, which is 0 before 0, and then it's just equal to the input after 0. This is the most classical one because it's completely parameter-free. There's absolutely no parameters whatsoever. But it does cause problems because there's no gradient whatsoever when the input is below 0. So it does have a tendency to make gradients vanish. Other activation functions, such as ELUs or leaky ReLUs, start having some parameters. So they increase the complexity of your model and the system you want to train. But they do improve your stability when it comes to training because they can compensate for problems such as gradient vanishing. You also have convolutional layers, and I'll go into a lot more detail on that. But basically, convolutional layers give you a spatial representation and puts together it takes an image and a semantic map of what the inputs are, and it tries to learn relationships, spatial relationships between those. And what they try to do is to really have a weight between, they try to put together the complexity of the input itself and how features are related in space, so that when you convolve with a specific kernel, you get an output that is meaningful from a representation point of view. You also have operations such as aggregation layers. So these could be things such as global pooling or max or min pooling. And convolution itself, and you'll see later on, it can also be used as a form of aggregation layer. And an aggregation layer is something that tries to summarize information in some form. And by summarizing information, the idea is that convolutional kernels only have a limited field of view. And by summarizing information, by aggregating information together, you can extend your field of view without massively increasing the number of parameters that you're trying to model. Right, so convolution, for the people that don't know exactly how it works, what you basically have is you have an input function, you have an input image, for example, or an input feature map, which has all of these variables, and you have a kernel. And the kernel itself has a dimensionality. So for example, in medical imaging, most people end up using relatively small kernels, 3 by 3 by 3 kernels. And what you're trying to learn is the weights of these kernels. So that's the part what people normally describe as representation learning. In classical machine learning, what you would do is you would represent your filter extractor. You could represent many of your filter extraction tasks as a kernel. For example, if you're trying to detect edges, there is a kernel, which is the edge detector kernel. If you're trying to detect corners, there's kernels that are appropriate for that. If you're trying to detect gradients, there are kernels for that. All of these kernels are nothing more than little matrices with numbers that apply certain types of operations on the data that transforms it to a subspace. Rather than prescribing what those kernels are, what we can do is to learn those parameters. So we start by randomly initializing those parameters, and then we backprop, we apply gradient descent, and we optimize these parameters so that they have a representation that is ideal for the problem that we have. And so this is actually pretty much key to the performance deep learning. So rather than us telling the algorithm what the algorithm should be looking for, is something that we humans like to do, but we don't necessarily know that that is the best representation. Deep learning learns those parameters one by one, and by learning those parameters, it finds a representation which is optimal for the problem you're trying to solve. So if the problem you're trying to solve does not require edge detection, you will not learn a kernel that tries to do that, for example. So it really is trying to have an optimal model for the representation and the problem that you're trying to solve. If you have this kernel, convolution is nothing more than weighted matrix multiplication. You take that weight there, for example, you multiply by A, you sum that with X times B, you sum that with Y times E and F times Z, and you end up with a convolution. So that kernel there, you multiply by each one of these elements, you sum that, and you basically end up with a response in that specific location. And then when you try the kernel, when you move the kernel to the next pixel, so when it starts in B rather than starting in A, you get that output. And when you move it to C, you get that output. So when you convolve this kernel with this input there, the output will be this matrix here, and is nothing more than vector-to-vector multiplication. Right, so how does convolution help us beyond just doing this? I think the most important part of convolution is that there's many different types of convolutions, and they're actually extremely important. Most of what's been happening in terms of representation has been around people putting together different types of convolution, because they do give you very different behaviors and very different performances. So standard convolution, as I was saying, is nothing more than taking a kernel. So in this case, this is a 3x3 kernel, and convolving it with that input image, the one in blue, and the output that you get is this one here. And you can see that when you do this convolution, depending on how you do it, and mainly if you allow the kernel to go outside of the input, you can have the output being of the same size as the input. Right? So this is what is called convolution with the same dimensionality or the same cardinality. If you wouldn't allow the kernel to go outside of the field of view of your input, of course the output then is going to be slightly smaller. And that's why, for example, in networks like UNet, the output is slightly smaller than the input. That's because you lose cardinality, because you're not allowing the kernels to see outside of the field of view of your input. But it becomes more interesting than that. So when you apply something that is called dilated convolution is something that is very similar to standard convolution, but the difference is that there is a spacing between the elements of the kernel. So what you saw here before is that you're applying W to A and X to B, right? So there is no, that gap there that you see between X and W is 0, and the gap between A and B is 0. But actually, if you say that W is applied to A and X is applied to C, you're saying that there is a gap between the elements of the kernel. And by adding this gap, what you're basically doing is you're seeing further away. So you're taking information that is further away, you're increasing your effective receptive fields, which means you're basically putting information together from elements in your image that are still semantically related to each other, but spatially more distant. So dilated convolution is a really nice way to bring context and long-distance relationships into a convolutional neural network. Then you have operations such as strided convolutions. So strided convolutions are pretty much the opposite of dilated convolutions. So in strided convolutions, what you do is you have a kernel that is compact. So the kernel the dilation factor is 0. So you basically don't dilate. The spacing between elements of the kernel is 0. But you only apply it every X number of pixels given the input. So for example, if your input here is 5 by 5, and your stride is 2, so basically you jump 2 pixels rather than jumping 1 pixel every time you apply the kernel, your output is going to be a 3x3 matrix. So you basically are going to reduce the cardinality of your problem by 2 in each direction. And again, why is this important? Is that if you think about it, strided convolutions are very similar operation to what pooling is doing. because it's reducing the cardinality. So in the same way that max pooling is going to take the maximum of a certain kernel in a certain location, strided convolutions can do the same if that is the optimal thing to do. But if there is another type of combination of inputs that gives you a better representation and a better aggregation of features, then strided convolution can learn that kernel that is optimal. So you can see strided convolution as a learned version of pooling. So by replacing pooling with strided convolution, you get the same behavior if that is the optimal behavior, but you can get a better behavior if there is better weights to learn. So all of these operations here either reduce the cardinality or maintain the cardinality, but you can also do the opposite. So if you have a strided convolution, so here we're talking about strides of 2. So every time we apply the kernel, we apply a stride of 2. If you think about applying a stride of 0.5 or 1/2, is the same thing as doing what is called a transpose convolution. So a transpose convolution, rather than applying the stride, the spacing that dilated convolutions have on the kernel, it applies them on the input, which means that you're actually increasing the cardinality. So you can think about transpose convolutions as a form of unpooling, right? So pooling is reducing the cardinality, unpooling will be upsampling the image, for example. And what you can think about in transpose convolution is really that upsampling process happening. So it's a way to bring up the cardinality of a system and increase the resolution of the activation functions. Okay. There's a few more building blocks that are a little bit more exotic. I'm not going to go into a lot of detail on them, but I think it's important that you're aware that they exist. Residual connections have become extremely important. So residual connections are nothing more than applying a little plus here. So when the filter extraction that you're doing, rather than learning the identity plus some other contextual features, the identity is propagated forward through an external loop. And you're learning basically a residual representation. And by putting together the input plus what is learned here, you can get something that is more complex. And you can think about it as, for example, if you're learning a function that is a sigma, for example, a cosine function with 2 different frequencies, you can imagine that the first function might learn a certain frequency. And then you pass that as an identity, which means that the representational layer can learn, for example, another frequency of what that cosine function could look like. And by putting together multiple sub-functions, you can learn more complex functions than you could if you were mapping identity. And also, because there are these shortcuts, gradients flow backwards easier because there is a gap. The gradients, rather than having to go through every single layer, they can actually jump backwards through these loops, which means also optimization becomes a little bit more stable. Then you have techniques such as dropout and batch normalization. They're not really the same thing, but they're 2 classes of techniques of things that you might want to do. So dropout is normally used as a form of regularization. So what it does, it deletes random activations, and by doing that, it creates redundancy in the network. And then when you are doing inference, you're actually run on the full network, which is the same thing as doing an ensemble of multiple subnetworks, all of them being independent from each other or being somehow redundant compared to each other. And more recently, there's a big hype about gating, attention, and memory, which is a way to focus networks on subsets of features or subparts of images so that the networks can have some form of introspection and summarize the kind of descriptors that they want to extract from the image depending on what is important for the task. So it's a way to basically train networks in a way that they're more intelligible also for a human being. So I want to introduce something that I normally is kind of an interesting way to think about this. So if you think about the classification problem, not the segmentation problem, so the classification problem where we're trying to map an image to an output categorical variable. The way you can think about it, when you see a network like this, the way I like to think about it is there are 2 big components. There is depth, which is the complexity and the complexity of the function you want to model. And there's scale, which is the cardinality or the scale of the input, the size of the input. So if you take an image, every time you apply some convolutions and ReLUs, then you do pooling, and then you apply some convolutions and ReLUs, and you do pooling, and you apply some convolutions and ReLUs, and you do pooling. Every time you're doing this, every time you apply pooling, you're basically going down in cardinality. You're gathering features from further away. So what you have is you basically have scale on one axis and depth in the other axis. And for you to go from something that is, let's say, 32 cube to something that is of size 1, because it's a single categorical feature, what you need to do is to apply a certain amount of pooling operations. And every time you do that, you're reducing the cardinality of your input more and more and more. And by doing that, you basically are transforming something which was initially a 32 cube input to something which is a 1 cube, or just 1, right? Is one single value. And then if you squish it through a softmax or an argmax, you get a categorical value out. But it's important to think about extractive features at scale. Pooling here is nothing more than giving you a sense of scale and gathering things that are spatially related to each other. If you now think about, so because each one of these operations has a relationship with regards to its cardinality between the inputs and outputs. For example, if the input is 32 cubed and you apply max pooling, the output is going to be 16 cubed. Which means that if you now give it an input which is of a different size, your output might not be 1 by 1 by 1. And if it's not 1 by 1 by 1, you don't get the classification. You actually get something which is semantic. So there are certain operations that do introduce cardinality invariance. For example, if you just do global average pooling, where you pool over every single element of your current representation, that can bring down the cardinality to the lowest scale. So even your input could be of any size, that as soon as you apply an operation like a global average pooling, it just pulls everything down to the cardinality or the spatial cardinality of 1. So there are operations that can introduce that kind of invariance. So many times you see networks that are only able to take images that are 256 cubed. And the reason for it is because they have this kind of construction. But if you were to apply an operation like that, you could take images that are larger than that, and you will still be able to do that, to classify them. Right. If you now look at the other axis, what you have is depth. So depth, the way you can think about it, is complexity of the feature representation that you have. Normally, what people tend to do is they start increasing the complexity or the width of the network, the number of elements, the number of features at each location, as you increase in terms of depth. And the reason for it is because your representation starts becoming more and more abstract. So at the beginning, because you're looking at a very, very local scale, you're basically detecting things such as edges and corners and etc. So there is a subset of things that are important. But when you then start pulling that information together and you start creating aggregates of the previous features, you're starting to get more and more abstract representations. And as you keep doing this, the representations become increasingly abstract. So the concepts that you're modeling are not just things like edges and corners. They're actually, for example, the gray matterness of a pixel or the tumorness of a pixel, which is a really weird concept for us. But the network tries to learn something that is compact and optimal. Right, so we looked into these building blocks, and we looked into the representation parts, but there's also things like loss functions. So just going, oh, sorry, I swapped the slides around. So optimizers, there's a class of optimizers which other people are going to talk about later today, but you have stochastic gradient descents, momentum-based, other grads, other deltas, RMS props, huge amount of them, all of them with different convergence properties. You have classic loss functions such as cross entropy and mean squared error. So cross entropy is what you would use for classification or segmentation. And for regression, you're just trying to minimize the L2 loss, for example, between the input and the output, or the predicted output and the ground truth output. But you have also some slightly more advanced loss functions, such as weighted cross entropy, which is nothing more than the previous one, but with a weighting term there. You have more advanced forms of dice loss. You have dice loss that is generalized in a way that the weights can make it invariant to volume. You have sensitivity, specificity losses. There's really a huge plethora of loss functions that you can apply that give you different properties to solve certain problems. Right. So we were looking into these little plots, these little tables of what classification will look like. But in a segmentation setting, what we're trying to do is map an input image to an output image, right? So the cardinality of the input and the output is the same. The only difference is that in segmentation, you're mapping it to RND, where D is a number of classes, while in regression, you're just mapping it to Rn, because you're getting a floating point value per pixel. And if you do that, basically, what you're doing is you're taking this representation here, where you're reducing the scale at every single iteration, and you're basically doing something that looks like this. So what this basically shows you is that the input and the output now are at the same cardinality. So you want the input and the output to be of the same number of pixels, right? But you still want to gather some information about scale. You want to gather features that are far away. You want to fetch that information. And so what you can do is to still apply pooling operations and go down in scale and then come back up, and the output will be of the same size. So this representation here, and you'll see later on, this is actually what UNet tries to do. So you have some set of convolutions, you shortcut that information, and you concatenate it with information that is going to come from that other path. And by going down in scale, you're gathering information from further away. So you get the benefits of having a high-frequency representation in the top row, which gives you very localized features, but you have something that is very abstract by going down in scale, and you have information from very far away. So, and you can see the similarity between this and this, right? So the shortcuts are nothing more than those lines. That concatenation element are those elements there. I didn't really have a symbol for it. And going down in scale and up in scale is exactly what the U from UNet is trying to do. So again, this is exactly what you'd expect. If you now go a little bit further, you can now start describing other networks within the same concept. So VNet, which is actually very similar to UNet, is trying to do something very similar, but the difference is that each one of these boxes is not just a standard convolutional operation, is what they call a V-convolution, which is slightly different. But more importantly, this last operation here, rather than just being a concatenation, is a residual model. So rather than that little box there, I just put the plus. Again, this is just to show you that they're pretty much the same thing. It's just small differences in operations. You can then go a little bit further. For example, if you have networks like DeepMedic, what DeepMedic does, it downsamples the image on one path, and it does a crop on the other path. And then at some point, it applies an upsampling operation. So it brings it back to the original cardinality, and then it applies some more convolutions. So you can think about it as soon as the input comes in, it goes down in scale, which is the downsampling process. You convolve, convolve, convolve at both scales. You upsample back, you concatenate the two features, and you basically end up with your output. So again, this representation gives you an idea that is always about playing with scales and playing with depth and trying to fit all of these two things in the memory of your GPU. Right? And they give you different levels of representation. You can go a little bit further. For example, you can have things like HighRes Net, where what it's trying to do is apply these contiguous residual connections, but each one of these convolutions is actually dilated by different factors. So when you dilate by a certain factor, you're fetching information from further away. So in reality, the convolution is happening at a lower scale because you're fetching information from far away, but the feature representation comes out at the high resolution. Right? So you're basically convolving at that scale, but activations are always stored at full resolution. So you end up with these high resolution responses, which is where the name comes from of HighRes Net. And again, you just have those series of pluses because it's just residual learning. So all of these networks can be learned, can be seen within this concept of just putting a series of operations together that are relatively simple, that try to aggregate information from scale and trying to store that deeper and deeper and deeper with more and more complex features. And of course, it's pretty much key to try to understand this concept well, because this is exactly where the representation learning gains its weight. It's very important that we're getting the right features at the right scale for the right problem. If we do not go, for example, large enough scales, if we don't go down in these plots enough, we might never see far away enough, which means if there is an important relationship, which is a long distance relationship, we need to be able to capture as further down as we can in this kind of plot, because otherwise we'll never learn that relationship. The network cannot understand that because he has never seen features from far away. Right, so if you now think about it, I just want to show you a regression example just to see what it looks like. So segmentation, you know it pretty well, but in regression, one problem that is very classical is taking an MR and transforming it to a CT. So this is the ground truth that you want to predict. And if you're going to apply multi-atlas methods, you get an image that looks roughly like this. And you see that he's not very good at predicting outliers and things that he has not seen before. Well, actually, deep learning networks are quite good at finding things that they've not seen in the training set. But this is nothing more than applying some representation learning, generating a predicted image, and calculating null to loss between the input and the output. So again, it's just a simpler regression problem. So now just to take you through a couple of processes that you need to go through. And this is kind of a little bit the tricks of the trade, or the art in the black art. So the first thing that most people tend to do to figure out if their network is doing the right thing is to just try to overfit on one example. If you cannot overfit in one example, probably there's something wrong with your implementation. So really, if you select a single image and you try to overfit, did it overfit? If it did not overfit, there's a few things you need to investigate. Are your weights initialized properly? Is the network saturating? If it is, scale down your parameters, right? Is, for example, the error loss bouncing up and down? Because if it is, in one single example, you don't really have any stochasticity, the gradient descent should be going in the right direction. If it doesn't, it means your learning rate is too high. Make your learning rate smaller. If your loss function is completely plateauing, maybe your learning rate is too small. Bump it up. It's a very good way to have an overall idea of how well your system is responding to the parameters you chose, to your implementation, and all of these other things. If it did work, what you can do is you can start adding more and more training data, right? And you can start looking into things like, has it started underfitting? And if it has, is there a way that you can increase capacity by making your network larger? Is it started to overfit? And if it has, can you improve your regularization? And can you start adding other things like unsupervised pretending or dropout to be able to make your model regularize? So there's a series of sanity checks that you should be doing the first time you try to solve a problem if you don't have a feel for what the parameters should be. And again, networks are becoming more generalizable, so this is becoming less of an issue because we're getting a much better feel as to what parameters should look like. Another part that is quite important is overfitting. So there's always a bias variance trade-off, and one of the things that you need to do is to try to avoid overfitting. And normally you do, the reason I talk about overfitting is when you try to fit a function to a set of training data, the loss function tends to keep going down, or it might wiggle a bit, but it tends to keep going down. But if you now run the same inference or run the same training on a separate validation set, what you see is that the error on the validation set starts diverging at a certain point. And this point where divergence starts happening is the point where you go from an underfitting zone to an overfitting zone, which means you should be stopping your learning there. So utilizing a separate testing set to be able to assess how your performance looks like is very important, because it's not just looking at your training loss function. Overfitting is really a problem. One way to go around overfitting, as you probably know, is augmentation. There's ways to create more data, and by creating more data, it makes your network less able to memorize inputs, and that helps quite significantly with overfitting. You can apply simple things like rotations, translations, elastic deformations, etc. But you can also apply something which is more meaningful from a medical imaging point of view, like histograms and MR physics, or noise models, or point spread functions, or artifacts, or pathologies, all of the things that you know your data is going to have and that you might not have captured well in your training data set. The other problem with overfitting is related with flat minima. So the interesting thing about flat minima is that your training set and your new image that you might get from your favorite clinician, they might not have exactly the same distribution. So their appearance might not be exactly the same. They might not come exactly from the same machine. And the problem is, if you were to train on that new image that you've never seen before, the optimization might end up in a very different solution. So if you are basically finding a very sharp minima, a very small shift in the loss function, in the distribution of your input, can have a massive effect in the performance of your new data set. But if you actually find a flat minima, variations in distribution and variations in the input data have less of an effect in terms of the performance of your algorithm. So again, finding flat minima is really important if you want an algorithm to be generalizable. Another part that people sometimes forget is to do hyperparameter tuning is extremely important. Most people say, okay, I use these parameters, but were they actually tuned or were they empirically set? And if you do hyperparameter tuning, if you do have the compute to do that, because you do require quite a lot of computational power, you can do many things such as grid search, just taking uniformly distributed values in terms of learning rates or depth of the network, or different algorithms like different learners that you might want to utilize. You can apply random search, so you just sample randomly parameters, and by doing so you can actually get better feel as to what are the best set of parameters. You can apply Bayesian optimization or any kind of sequential model-based optimization where you learn on a set of images, you validate on the test set, and you try to figure out, utilizing the test set, which one was the best set of parameters. So there's many things you can do, but please do focus on hyperparameter tuning. And the reason for it is because if you try to solve, for example, a two-dimensional problem, so this is a matrix. This is a matrix showing two different networks and different loss functions, and how the performance varies according to the size of the input patch and the learning rate. And you see that the performance varies quite massively. So if you don't have the right parameters, you might not be learning the right thing. In 3D is even worse, because the dimensionality of the space grows, and because of that, it gets really tricky to optimize. So you really need to get the right parameters in the right place and the right loss function. And you can see that is not very linear. When you change the loss function, then you change the network, the parameters can be really, really different. So just to try to finalize, There are some tricks to the black art, as people normally say, that you cannot forget. Normalizing your input data so that it is relatively in the same range is very important. For example, if you train your data to be all between 0 and 1, and then a new image comes in and it's between 0 and 255, your network is probably not going to perform well. Apply decaying learning rates. So for example, if you train a network for a while, you might be learning relatively fast, so the loss function goes down. But when you're close to your convergence point, you can actually get quite a lot of performance by slowing down your learning rates and getting a slightly better minima. You can do mini batches. In medical imaging, sometimes it's tricky because it doesn't really fit your GPU, but if you can do mini batches, it does introduce some form of regularization for problems that can be very tricky. You can have gradient scaling learning methods. So rather than just applying stochastic gradient descent, you can apply more complex operations that do scale each one of the gradients for each one of the parameters in different ways. And all of these things can help the convergence. And I just wanted to finalize by giving you a couple of examples to show that segmentation and regression are kind of the foundations for many other things. And many of the tasks that we actually want to solve in medical imaging, at least the more classical ones, not necessarily the ones that are going to be solved in the future, but the ones that we've been trying to solve for the last 10, 15 years, are all pretty much a very big regression problem. For example, you can think about registration as a regression problem, where you're trying to regress deformation fields, right? Registration is nothing more than saying, given two inputs, what is the transformation between them? Again, that's regressing a floating point value that just happens to be the x, y, z deformation between the input and the output, right? That's one way to think about the problem. And I'm going to skip a couple of parameters because I'm a bit late. Another part that you can think about, for example, we were talking about cardinality and about transforming inputs into outputs. But what if your inputs are missing, for example? There are ways that you can apply abstraction layers. In this case, this is nothing more than taking mean of multiple representations to say, if, for example, this modality here is missing, I'm not going to have any activations there. But when I'm calculating the mean over these elements here, the mean is actually an invariant transformation to the number of inputs. So your network can become invariant to missing inputs. And you can get a really nice performance decay between different images transformed with different inputs. And just to finalize, another part that is now becoming quite trendy is to look into uncertainty of networks. So dropout, even though initially was utilized to apply as a form of regularization, recent work has shown that it actually can approximate quite well the variational distribution of possible outputs of the models that are encoded in your network. So given that specific architecture, you can perturb it by learning with dropouts, and then at inference time, you can pass through multiple subsets of dropouts. So you can basically mask your neurons in multiple different ways. And every time you apply a different neuron mask, you're going to have a slightly different answer. And by having a slightly different answer, you can then have an estimate of variance of those outputs, right? And by doing that, you can actually get a feel for what the network knows and what it doesn't know. So if there's a problem that the network has never seen before, the outputs are all going to be very varied every time you apply a new mask. While if the problem is very stable, all of the outputs are going to look like the same. So by doing this, you can basically get some idea about the uncertainty of the problem. I'm going to skip all of that. Right, so just to conclude, image segmentation and image regression are actually very, very simple problems. Loss functions are extremely important, mainly if the problem is highly unbalanced. And the things that you really cannot forget is, don't forget to appropriately split your data between testing, validation, and holdout sets. Don't forget to do hyperparameter tuning, really important. Augmentation tends to be key in medical imaging because we don't have very large data sets. And you can actually go around a lot of the problems by applying appropriate augmentation. Do schedule your learning rate. It will improve your performance quite significantly. And don't forget to regularize your network if you want to have something that is truly generalizable to new data sets that you might not seen before. Yeah, thank you.